First order of business. Will anyone not here please raise their hands? Okay, that's good. We've got 100% attendance. That's the first item of business. I'm glad of that. Anyone here who's not a member of the Grand Rapids Amateur Astronomical Association? Now, yeah, you need to sign up. You know, come on, you know. So go online, nice little online application form. You'll get regular notifications through email. We've got a nice little, group email blast that comes out periodically. We try not to do things like I've subscribed to Home Depot, and my gosh, if I don't get 3 emails a day, they're falling behind. Yes. The inbound income, the income is never closed. Yeah, we're always open for business on that. Second, okay. By the way, I'm Chris Miller. I'm the president of the Grand Rapids Amateur Astronomical Association, and I'm getting good at that. I can say it almost 3 times in a row without tripping over it. But I just wanted to welcome you to this very special event this evening. And in this very special environment, this is a great resource that we have here with the Grand Rapids Public Museum, and a great relationship that we have with them. And being able to use the Meyer Theater here is one of those benefits. And it comes to us at the right price as well, and I just wanted to say, in terms of membership, those, I'm encouraging those who are not members yet to go ahead and sign up as an individual. It's $40 a year. And, well, wait, there's more. If you have 2 or more, you can sign up for a family membership, which is only slightly more. So you can get 5 for the price of 1. I got more. This is the 4th quarter of our fiscal year. So sign up now, you're good until 2026. Till June of 2026, yes. Yep. So, okay, as a matter of fact, and our membership continues to grow, by the way. We're coming up close to 400 members in our association, which is continuing to be good news. Now, okay, that's membership. I also wanted to just bring attention to, we are getting ready to start our, our revolving door of events, public visitor evenings. Our first one is this weekend on Saturday evening, and it's going to begin with what is called a telescope clinic, where at 8 p.m., if you have a scope that you bought or have and you're having trouble using it, bring it on over. We're going to be open early, and there'll be a few of us out there, a few techies. I mean, I even come armed. I've already have my multi-tool on me. So to help you work through any issues that you're having. I could use some help with my own scope. I'm having trouble with a USB port on it. But anyway, we'll go on to that. We don't have the advanced telescope clinic. And on the 10th of May, we're going to start something new. And as a matter of fact, the instructor here, if Kurt would stand up there, Kurt is going to hold a little, we're going to do a couple of sessions with basic digital imaging. And he's going to hold the first session on Saturday morning at the observatory. It'll be a special surprise. I have no idea what the content is. But for a repeat performance, if you're not available on Saturday, he's going to offer it again on, is it Tuesday evening? Yeah, at 7:30, again at the observatory. So if you can't make the Saturday, you could make the Tuesday. So for those who kind of want to get started, it's an introduction into, there's so many flavors of doing digital astronomy, but Kurt's going to introduce a couple of methods that he thinks will have some appeal, and so give it a try. And so we hope to grow that as we come up. So that's all I just wanted to mention that are the next few upcoming events. If you come up to the hill, by the way, you're going to see that our inventory of scopes is increasing now. We now have what is called the Strickwood Annex. It's an additional building. It looks like a 1.5-car garage, except it's got no door. Well, that's because the roof rolls off, and we have 4 scopes inside. So we have one building with 4 scopes. And we're going to be And that brings me to another topic, which is training. We're going to be introducing training for the various scopes that we own, and Dave DeBrian's going to be helping to organize that. And we're going to introduce a system of tiers, as we call them, because we've got multiple scopes in multiple situations, and so we're going to start off with the simpler telescopes, provide training for that, and then you can advance to the next tier and do a little more training on some other scopes that we're going to have. So I'm looking forward to that, and as we get our equipment online, we're already working through some things. We've reworked our Bohr telescope, the one that's over in the West Dome, and that's going to be coming online here pretty quick. We've got a couple of scopes down in the Strickwerda Annex, and then I'm going to, hopefully this summer, I hope to have the telescope in the East Dome that we call the Marin scope coming online. Okay, I think that's enough about me. What do you think about me? Okay, enough of that focus. Okay, I want to bring focus on our the man who's going to introduce our speaker tonight, the former director for, I don't know, half a century, no, quarter century, how many years? Long time, director of the planetarium. He is now the director emeritus of the planetarium. Dave DeBrian.
Thank you, Chris. Thank you very much for all you do for this organization, which is no small amount. If you are interested in our activities and becoming part of us, we have the annual program book, and I have some extra copies outside by the display board, which also shows you a nice picture of some of our latest advances, some of our newest facilities at the observatory. So we hope to, if you've never been up there or visited with us, we hope to see you there this summer at some point. And those of you who are on teams for various functions for the public nights, pay attention when the chairperson for your team sends you an email or a text. Please respond, and please respond favorably so that we can fulfill all of the necessary requirements for bringing astronomy to the public in a very efficient way at the observatory. We get 4 stars plus repeatedly. Just read some of the reviews of the experiences at the observatory to appreciate what our hard work results in so far as the public perception of the Astronomy Association and the observatory. In thinking about how to introduce my longtime friend and former colleague, Jake Bourjaily, it became immediately apparent that if I went through his bio, there'd be no time for him to talk. Besides, I think most of you know how to read, so all you have to do is Google his name to find an impressive list. Don't do it now. You would find that Jake grew up in Grand Rapids in the late 90s, became a student leader in GRAAA, and an intern producer and show presenter here at the Chaffee Planetarium. You would also learn that upon graduation from high school in 2002, he won the prestigious Roger B. Chaffee Scholarship as one of the area's most gifted science students. Tomorrow night, he'll be a featured speaker for a dinner honoring the 58th recipient of that prestigious award, which began in 1967, the year of the spacecraft fire. And you would also be pleased to know that the winner of that prestigious award for this year is Samantha McClellan. You can't find her in the dark now, but she's out there, who we are proud to say is a student member of the GRAAA. She was part of a select group of fellow GRAAA students at an informal meeting with Jake prior to this event this evening. The kids are full of pizza, so if you're sitting next to one of them, be sure to poke them once in a while to make sure they stay awake. You can read online that following graduation from the University of Michigan, Jake studied abroad as a Marshall Scholar before returning to the U.S. to complete a PhD from Princeton. Then it was on to Harvard and a post as graduate junior fellow, or postgraduate junior fellow, where he met some of the world's leading physicists, started a long string of scientific papers, and began work as a collaborating author of the book. Are you ready for this one? Grassmannian Geometry of Scattering Amplitudes, published by Cambridge University Press in 2016. Page 2. There's only 3. In 2014, he departed Harvard for the Niels Bohr Institute in Denmark, where he led a team of researchers in the realm of quantum physics, staying there until returning to the US in 2020 to accept an appointment to the physics faculty at Penn State. It is there that he met his wife, Tasha, who, it appears, finally convinced him to curtail the constant world travels and to settle down to a more conventional way of life. As he admitted to me when we were driving over here this afternoon, he's now, as the father of 3 daughters, and will become a full professor at Penn State this summer, so he's pretty much ensconced now in one place, at least for a while. Okay, we just determined that Jake's a pretty smart dude. Allow me to conclude by recalling some incidents that illustrate that Jake is not just smart, but exceptionally well-grounded. And he proved that again tonight with the kids. Very, 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 with a punctuation mark. These are things that stand out to me personally and contribute to why he is so widely admired and respected. I remember when he first burst onto the scene. Jake wasn't so sure he remembered that, but I do very clearly. Occasion was a holiday party that my special friend Donna Denbohr and I, along with other advisors, hosted probably somewhere around 1998 or so for the GRAA student members. Jake was either in the 8th or 9th grade, but was so at ease and so poised, fitting in so well with both his peers and those much older, obviously very mature for his age. As Donna and I were cleaning up after the event, she said, "That Jacob kid, he was really something." How prophetic. Jake started helping out at public nights at Veen Observatory. Another thing that I pointed out very pointedly to the youngsters this evening, soon tiring of having to trudge up and down the entry drive with baskets of flashlights, which we issued to visitors navigating the dark road from the lower parking lot area to the observatory. The result, a well-prepared proposal to the board to pull together a team of fellow scouts and volunteers to install a series of confidence lights along the entry drive as an Eagle Scout project. And of course, it goes without saying that he attained that rank of Eagle Scout very easily. And we go on to the next page. Who among us, those who work and visit the observatory, have not benefited from the foresight of his Eagle Scout project? I mentioned that we quickly hired him at the planetarium while he was finishing up his last 2 years of high school. He became well known for his articulate sky show presentations and for his creative abilities. It did not take Jake and the other young staffers at the planetarium long to get involved in, you guessed it, Pink Floyd light shows, which drew big late night weekend crowds and definitely helped to pay the bills. Jake threw himself into the creative challenges with great relish, noting that it was a nice diversion from figuring out how the laws of physics govern the universe. One morning, as I came into the museum to start my day, I was greeted by a security officer with a serious, very serious look on his face. "Did you know there were a couple of kids up in the planetarium almost all night? They just left about an hour ago. They had this really loud music going and were playing with the computers and all the other stuff," he said breathlessly. The kids said they knew that you knew about it. Well, yes, I did, I replied. Jake told me that he only sleeps when there's nothing else to do. Someone later asked me, do you really trust those high school kids with all that expensive equipment? And my response was, there's really no reason not to. Finally, this story, which is really quite personal. For decades, I've hosted a pre-Christmas open house at my home for valued former and current colleagues at the planetarium and GRAAA friends. Jake, of course, is always on the invite list, but in recent years, his travel abroad had limited time back in Grand Rapids with family, had prevented him from attending regularly. I lied, there's one more page. Only a half a page. Sorry about that. I've only had 60 years experience handling a microphone. Oh well, I've already read that page. Okay, this must have been about 5 or 6 years ago when he surprisingly showed up at the holiday party, much to the delight of those gathered to make merry. After some glad handing and exchanging of greetings, Jake kneeled right next to my friend Donna, who was now in somewhat failing health, but beaming to see her again, someone she had admired so much as a kid. There, for an extended period, Jake concentrated the conversation not on his latest world travels or scientific endeavors, but on Donna, her life, and her challenges. And Donna recalled that over and over again, more than once in the years that followed. And I just wanted you to know that, wherever you are, Jake, and also his family who's here tonight, that is just a great testament to the character of this young man. One night, Donna and I even sat down and tried to comprehend at least the prologue to the copy of that book that Jake co-authored, which we quickly determined is directed toward fellow scientists. Oh well, we tried. Jake's most recent honor came just several months ago when he was named 2025 recipient of the prestigious Lars Kahn Rasmussen Prize from the Niels Bohr International Academy as a leading young scientist. He's also a great communicator of science. After all, he got his start in the Chaffee Planetarium. And more than anything, is a great person. That's why I promise you that you are about to hear is going to be worth every minute of your time. Please stay after for a meet and mingle session in the lobby outside the theater. And we are even going to kind of coax you there with some punch and cookies if you behave. Jacob, finally, it's your turn. Welcome.
All right. Thank you again. And thank you for the benefit of the doubt on this talk, because it's a big subject, and I've been working very hard to try to to tell a story that I hope you'll enjoy about why I think that fundamental physics is a very exciting field today, and in particular about our understanding of fundamental physics. Because throughout the history of science, the meaning of this phrase has varied from time to time, and that's part of the story I want to tell today, is about the meaning of the phrase fundamental physics and how our understanding of it has changed, and why I think this is a very special time right now. And of course, to give you an adequate picture of what's going on in fundamental physics, I have to review some of the basic laws, and I'll start with classical physics. I promise this should be fairly accessible. And by the end, I hope you will understand some quantum field theory and what's going on today. So the questions in fundamental physics are in many ways the grandest and the most fundamental, well, the most fundamental, that sounds terrible. The biggest questions about the universe as a whole and the smallest constituents of matter and the most basic rules. But on many levels, it's an extremely limited set of questions. Not about how many systems of atoms behave or life and things like that, but the basic rules, the most fundamental rules. Well, I'll give you a sense of that. So when we look out at the universe from the Veen Observatory, or really anywhere in nature, we can see that the world around us is filled with a variety of phenomena. The stars, the sun rising and setting, and the moons, planets. But there's also the wind and the sounds. There's the observer, happiness, and thought. There's a lot of variety in the world around us. And part of the goal of fundamental physics is to try to make sense of all of this variety of phenomena in as simple possible terms we can, in the most microscopic way, in the most simple things. And so, it's very ambitious. The history of the universe from the Big Bang to today, but also how do all of the, what are the rules that determine the motion of not just the planets, but also the things around us, the material around us. And the history of science, and I'm not going to talk through all of it, but this story is a very beautiful and rich story, going from the big discovery of the chemical elements by Mendeleev to our understanding today. This has changed. When I was lecturing here at the planetarium, I remember teaching that the elements were all made in supernovas, but that's not true for over half this table anymore. But also how the atoms glue together. This is my daughter Allie building a double helix. How do the atoms decay? What are the rules of electricity? And Marie Curie discovering polonium and radioactive decay. The full chart of the nuclides. Today we have a great understanding of all of these elements, and I teach a class at Penn State about that's half related to this chart of the nuclides, which is the refinement of the periodic chart. But beyond the elements, it was discovered about 100 years ago that there were other particles that appear in nature. First from cosmic rays, that if we look out and we put originally through balloon experiments, that we would discover all sorts of a variety of interesting particles, smaller than elements, that behaved in interesting ways. And in the process of trying to understand their behaviors and how they work, we built giant machines. This is the big European bubble chamber at CERN, and this is a picture of a beam of kaons, I think, spinning through magnetic fields. And today, we have the last century has been a real triumph in our understanding of these basic constituents. Through enormous investments and enormous experiments. This is the Large Hadron Collider at CERN, at the Center for European Nuclear Research, where it's a 17-mile ring, half a mile underground. To get a scale of some of these experiments, they always put a person in one of these pictures. So there's the person. This is about 7 stories tall, these experiments. And there are the people there in this giant chamber here. And today, the culmination of all of this enormous effort has been what we always capitalize as the fundamental or the standard model of fundamental particles and their interactions. And this is not the story I'm going to tell you today. This is a story I teach my students. It's a particular quantum field theory, but it's not exactly the story I want to tell. So historically, the fundamental physics, the goal of fundamental physics has been to address the constituents of matter in our universe. What are the laws that affect us, the universe we see around us? And that's a very beautiful story and a very rich story, and it's one that I think is still continuing, but one that we've made tremendous progress in the last century. Last century was the century where we discovered the standard model and we understood these basic constituents, and it's an amazingly refined, accurate description of the world around us. That is not the story I want to tell you today. The story I want to tell you today is a little bit more subtle. It's about our understanding of the laws, the fundamental laws. And to get a sense of that, I need to go back to the beginning and to give a sense of what fundamental physics has looked like over time and how it changed several times, the pictures we have in our heads for fundamental physics. And there's no better place to start than with Isaac Newton and his system of the world. In the history of science, there are very few publications quite like this, where just out of nothing comes 3 volumes that change the world and change our understanding of basic science. This is a picture I took, by the way, of his first edition, his copy of the first edition, where he crosses out member of the Royal Society and writes president for the second edition. Very little vain. Well, in it, he laid out the laws of motion. And the first one he lifted directly from Galileo, which is inertia. That if something starts moving in a straight line, it'll continue to move forever and always in that straight line, same speed, unless, and the second law of motion is force, that if forces act to change that motion. This is like one of the only equations I will have in this talk, but force is equal to mass times acceleration. It's very easy to understand that if you apply a force, it will change your motion. So things are inclined to keep moving with inertia forever and always in a straight line, and if you apply a force, it will change. But that change depends on the mass. So if you apply the same force to a baseball, it'll change its velocity quite a lot, and if you apply the exact same force to a bowling ball, it doesn't change it quite as much. Okay, but this is only useful. It tells you what will happen next if you know what the forces are right now and where all the particles are, where all the masses are, and it allows you to predict the future. But you need to know what some F's are. You need to know what M's are. And he only gave us one law of fundamental, at least, that falls in that category, of force, which is the law of universal gravitation, that everything in the entire universe attracts everything else with a force that varies inversely as the square of the distance. So the further away you go, it dies down, and it points in the direction of between the things. And so if you knew that a planet was sitting here, and it had a velocity here, and it's attracted to the sun's also attracted to the planet, but not by very much, that you could determine what happens next. And then if you looked at it again, you could see that it's moving this way now, and there's a force moving that way, and it'll change its motion, and it goes there. And now the force is higher because it's closer to the sun. And at every single instant, you can go to the next instant, you can step forward, and you can figure out what will happen next and predict the future. And it was a great success of Newton that he was able to show that, say, Kepler's laws followed from this force law. But if you have studied physics, you will know that this is hard. And in particular, this involves calculus. Adding up, that is what calculus is. It is adding up all of these little itty-bitty forces at every little instant of time and then making the moments closer and closer and closer together and solving these equations to see where the motion is. And that is an important aspect of the quality that I'm not going to talk about very much, but that's the kind of math that's involved, which is adding up all of these little itty-bitty forces. But it's a very causal picture. You understand at every single instant, you know what's going to happen next because you know what's happening right now, and you can run the movie forward. I want to pause and just emphasize that that unlike Kepler's laws, which said that planets orbit in ellipses and the sun is at a focus, Newton's laws is in many ways simpler because it says that everything attracts everything else. And in particular, the Kepler orbit doesn't need to be true because, for example, what if the planet happens to go by another planet? That's in fact how the planet Neptune was discovered, was its variation. Uranus was seen to slow down a little bit relative and Leverrier had predicted that there must be a planet behind it to slow it down. So it's a very simple law, and things like Kepler's laws only come as approximations. Now, this is in some ways a story about calculus, but not about calculus, but about the way we picture Newton's laws as working, as adding up every little force. Because a very interesting thing. Now, I talk to a lot of physicists, and I'm just coming off of this century of great discovery of the laws that apply to our universe, the creation of the standard model of particle physics. And people talk about it was so amazing when we discovered all of the fundamental particles that we see in our world. But I often have to remind them that in the 100 years after Newton, not a single new force was discovered. There were all sorts of approximate forces, like friction, that nobody really understood. But gravity was the only one that was thought to be fundamental. However, there were great physicists that came after Newton, very great physicists, who didn't discover a new particle or a new force of nature. But they did have radically important ideas about science, and really about the way that we thought about Newton's laws. And the most radical of which has got to be due to this gentleman, Euler. I was also put him on money. This was my driver's license, or sorry, license plate when I lived in Michigan. But he had a radically different idea. That basically you could determine how a particle moves, or a planet moves, or anything, really. You could understand Newton's laws in a very curiously weird way. Basically, don't think about forces. Don't think about forces. Instead, just imagine that the planet takes any conceivable path. And for every one of those paths, use some calculus and calculate a number called the action. And the different numbers will be bigger or larger. Anyway, the planet, turns out, it takes the one that has the smallest number. Now, if you would have asked Euler whether or not he thought that that's how planets moved, like that they smell around all their conceivable possible paths and they find the one they like the best, he would have said you were crazy, right? That doesn't feel causal at all. There's no notion of time evolution, nothing like that. It seems completely crazy. And Euler was a very pragmatic and mathematician. He would have been completely satisfied by telling you that it was a theorem that the motions of things using this silly rule give you exactly the same as the consequences of force equals mass times acceleration. I'm going to come back to this because we're going to see that actually today we still teach our students this sillier idea for two reasons. One is because it makes the math a lot easier in a lot of ways. The other reason is because we actually think this is deeper. This is actually closer to the truth. I'll have to convince you of that in a little bit. But on a mathematical level, they give exactly the same predictions for how the world works, but they're very, very different pictures. This is the kind of revolution that I think we're going through right now. In terms of fundamental laws, there aren't that many classical fundamental laws, and the next one took actually quite a long time to work out. But it's kind of easy to see how powerful it is. So you imagine a force that's analogous to gravity, basically the same equation, although with actually two very important differences. The first is that unlike gravity, where everything in the universe attracts everything else, you have two different kinds of things, and the likes repel each other, and unlikes attract. Okay? So different ones, if you have two kinds, red and greens fly into each other. And as long as the charges or the strength of this attraction and repulsion are the same, if you bring another particle nearby, it basically can't tell that this thing is charged at all. It can't tell the difference because the attraction to the red one and the repulsion from the green one kind of cancel out. So that means that from a distance, you really can't tell that this thing just looks neutral. It basically has no effect as a force. And if you imagine that there's a force, and it's enormously more powerful than gravity, then different kinds are going to stick together. And the things that stick together we call atoms. Okay? But it's enormously more powerful. By the way, thinking about atoms turns out to be a really good idea. Even before you know anything about how atoms work or how they look. But it turns out the idea of thinking about gas as just a bunch of balls bouncing around easily helps provide a very quantitative understanding of how to build an engine, how pressure works and temperature and all that stuff, and sound or waves of pressure, excess density in these waves. It's a very good idea, this idea of atoms. But I want to give you a sense of how absolutely enormously more powerful this force is relative to gravity. Sometimes I remember, one way to think about it is that the entire Earth is pulling you down. The entire Earth is pulling you down, and just a couple little atoms on the surface of the ground are holding you up. But to give a better sense, imagine taking one single grain of sand, and if you were to separate all the likes apart from the other ones, so the two different kinds of things, and you separate them and you put them a yard apart, the force of attraction would be 41 billion tons. That's how much they'd want to stick. Okay, there are a lot of big numbers in this talk, so I try to make them plausible, more something you can wrap your head around. That's 4 million Eiffel Towers, the weight of 4 million of them, which, by the way, would be a tower of Eiffel Towers that would go all the way up to the moon and back to the moon. And then if you were to separate these things and you let go, the force of attraction would be so much, they would slam into each other with such great energy that it would be 3 times the first atomic bombs, 90,000 tons of TNT. So big. Okay. Now what does the world look like? So the world looks like atoms stuck together, which are little neutral things, because from a distance you can't tell. The attraction to one and the repulsion from the other kind of cancels out. And the only thing that really distinguishes them is how many different kinds of things are stuck together. And indeed, we can understand the entire periodic table. If you have a single pair, we call that hydrogen. If you have 118 pairs, it's called oganesson. And it turns out it's really hard to put more than 118 things together to make an atom like that. But it turns out the entire Mendeleev chart, the periodic table of chemistry, can be understood as just different collections of how many pairs are stuck together in these atoms. Okay. And we call, when you take groups of things with the same number, we call it an element. And when you have different things of different elements stuck together, like in this model of deoxyribonucleic acid, the different colors here represent different kinds of atoms, and that we call those molecules. Now, it turns out that actually understanding this force law was very much complicated by a couple things, and it took 60 years to really work out. The first thing is due to Ørsted here, which is that if you have a moving charge, you just move it around, it makes a magnetic force, and changing magnetism causes electric forces. So it's all very confusing. And the feedback loop creates light, which is a nice thing to understand. Well, I'm not really telling you how atoms work here. But I want to emphasize a couple things, because this is going to lead into the next big revolution in the way we think about physics, which is that these unequal these parts which are attracted to each other, these two different kinds of things that form atoms, are extremely unlike. They're very different from each other. The red ones, the one kind we're going to call protons, the other kind we call electrons. You know this. I'm sure everybody knows this. The protons are extremely small. I'll give you a sense of that in just a moment. But the electron is funny. You can read in any textbook, it's point. What does that mean? Well, it means it's so small that nobody can see its size. It has absolutely no size as far as anybody can tell. It's not small, it's nothing. It's just a point. And a proton is very small, but it is absolutely not a point. It totally has a size. It's a very small size, but it has one. To get a sense of this, by the way, if you were to take a normal necklace, like, one that you'd hang around your neck, and you were to string it with protons, you would require a quadrillion of them. Okay, a quadrillion is a number you can't think about because it's too big, but 1 quadrillion, if you if you were to blow up those protons to be the size of a strand of hair, it would wrap the Earth 10,000 times. Okay, that might not help you. They're very small. And also, these things are way, way heavier. The electrons are very, very light compared to them. So the imbalance is such that it would take almost 2,000 electrons to balance the scales. 1,836, more accurately. Okay, so it's a very unbalanced system, and it might remind you, some of you, of like the solar system, say. The sun is very heavy, the planets are very light. But now something that fundamentally would screw up our understanding about atoms was the fact it was discovered that they are very big. In fact, atoms are so dramatically bigger than a proton that it makes almost no sense. So if you were to take an atom and you were to blow it up so that the atom were the size of, say, a mile across, the proton sitting in there would be less than an inch. Okay? Less than an inch. It's hard to show that accurately to scale on a slide. By the way, the nucleus has another kind of thing called a neutron, which basically weighs basically the same size. A little heavier. It's actually really important it's heavier, but it doesn't matter. Okay. But this is crazy, because what I just told you about these things attracting each other would easily let you suggest that they should be sticking on top of each other. And they are not. You think, oh, well, maybe the sun, like the planets. Maybe. But just like the suns actually the planets radiate some gravitational energy when they orbit, and eventually, if you ignored the fact that the sun will explode and other things, the Earth would eventually fall into the sun. The same thing happens to these electrons. They are attracted to the center. And in fact, you can easily, well, not easily, but you can do the calculation. Students of physics will do it. Anyway, how long would it take an electron to fall into the nucleus? And it turns out 1/100 trillionth of a second. Less time than it takes light to cross the human hair. That's how unstable atoms are. So all of our understanding of electrodynamics would suggest that atoms should be the size of protons. They should be stuck together, and they are not. And I wish I had time to explain exactly why what I'm about to tell you solves this problem, and I do not. But I hope you appreciate that our understanding of classical physics, what I've been talking about, fundamentally can't explain the atom. And that understanding the atom would require some really radical changes and profound changes to their basic understanding of how the world works, and ultimately lead to quantum physics. Now, quantum physics is a subject that I think gets a bad reputation, and it's really not that bad. It might bother you philosophically, but I promise you it's true. It's the way the world works. And it's very easy to appreciate and understand how it works. You can almost do this with your own eye. But the idea, everything about quantum mechanics can be understood as a consequence of this very simple experiment, which is that you shine some light, a laser, say, through some slits. And I've got a little CD. These are almost antiques now. And you can shine it up on the board, let's see, or on this thing. And you can see that there are dots. This is reflective instead of transmittive, but whatever. You can see that there's, okay, come on. Okay, see there are dots. There are some places where the light goes and places where the light doesn't go. This is a very well-known phenomenon. Has been known for hundreds of years that you could make these kinds of interference patterns, and it's very easy to understand. So the intensity of the light can change from place to place. And it was very easy to understand from the wave, the idea that light was electromagnetic waves, and that waves interfere. You can do this with water. It's very easy to see that the crest of one wave will cancel out the trough of another one and get nothing out of the bottom. All of the problems of quantum mechanics come from the fact that I can dim the light. Because when you dim the light, if you turn this down, what you will see is that bright light does not mean waves. What it means is that there's lots of bits of light. And the human eye can almost detect a single bit of light. It's actually like an interesting little biophysics kind of problem that it is almost statistically significant that a human being can see a single photon. But anyway, it turns out that photons, like everything else, comes in lumps. And this intensity thing that we were just talking about is not about waves interfering, because you can turn down the intensity of the light so much that maybe you only get one piece of light coming through per hour. And this is really not an intensity, it's a statement of probability. And that screws up your whole way of thinking about the world. Okay? But by the way, just to understand how hard it is to see individual photons, imagine how bright things are. So my laser pointer here is 134 with a lot of zeros, photons per second. A single pixel on my phone, I looked this up, was 175 trillion photons per second. So you really got to dim the light, but it's impossible to do, to see individual photons. It's basically right at threshold. All right. Now, what's funny about this is that it's actually relatively easy to understand the behavior of these things by thinking about them as smelling around all their favorite paths. This idea of this computing some number. But in this case, the number has to be like a wave. That's weird. But the idea is that if you imagine the photon is trying out all these different paths that it could possibly take, then it can interfere. And so sometimes you can imagine like a very smart, so like what happens if I put another hole in here? Well, you could imagine now you have interference from 3 paths. What if I put another wall in? Well, there's lots of different ways of interfering. All those things can be understood from waves. But what if you have a wall with an infinite number of holes and an infinite number of walls? And what you get is you get all possible paths from here to here. It's looking a lot like that weird idea of Euler's. Okay. Which is one of the reasons why we think it's more fundamental. And I think I can summarize the principle of quantum mechanics very simply. And sometimes people talk about wave-particle duality, all sorts of confusing things. If you've heard any of those things, I don't think of it that way. I don't think people think of it that way. First principle is that things are particles. Everything in the world, light, everything you might have thought was a wave, no. Everything is particles 100% of the time. They're quanta. Things come in lumps. There's either a photon there or it is not. Every single time, 100% of the time. Things are particles. Okay. Second is that the universe is such that we are not allowed. It is impossible for anything, including the photon, to know what's going to happen next. There is no causality. There's no deterministic future. I can't calculate what will happen tomorrow from today. All I can do is calculate probabilities. The world is deeply intrinsically, at its core, undeterministic. It's probabilistic. It's a random thing, but it's not random in like some vague philosophical sense. It's random in a predictably random way, and we can test these probabilities. And it turns out that from this point of view, and the probabilities can interfere, like waves. Okay. Now, from our view of quantum mechanics, classical physics is a different kind of statement. It's telling you about the most likely thing to happen next. And in many circumstances, the most likely thing is billions of times more likely than the next most likely thing. In which case, you might as well just ignore the whole probability thing altogether. That is classical physics. It's very funny. And it's something that people have a hard time wrapping your head around. But once you get used to it, it's like, OK, I calculate probabilities. That's fine. All right, I can do that. And the version of calculus that deals with probabilities is called quantum field theory. And I'm a fan. This is my car, my current license plate, QFT. It might have gotten me out of a speeding ticket once. But quantum field theory is just a set of mathematical tools, like calculus, that allow you to calculate, to make probabilistic predictions for the future in some context. So what I mean by the context, is what are the Fs? So you have to state a theory, a quantum field theory. The standard model is a particular quantum field theory. But it turns out, and this is very curious, my students hate to learn this, that it was invented independently by financiers in the 1960s. It's called the stochastic calculus, and they used it to make pricing models for how valuable your home should be a year from now. It's a very probabilistic prediction, and it depends on all the possible scenarios that happen between today and next year. And so it's the exact same math. It's a very simple kind of set of math. It's not very easy, but that's a different thing. The point is that it's just math. It's about calculating. It's like using calculus to calculate the future given present using force and mass. So it's a language in which we describe the fundamental laws, and it's definitely the picture we have for our fundamental laws of nature. But it's also the same set of math that we would use for any imaginable world governed by quantum mechanics, or any system where you choose to ignore stuff, so it becomes probabilistic by default. So quantum mechanics there's no ignoring it. The electron really doesn't know where it is. That's hard to come to terms with, but that's true. But in lots of systems like the stock market or biological systems or semiconductors, you just lose track of stuff. And when you lose track of stuff, it becomes a probabilistic question about like what's most likely next. And as soon as you do that, you get into quantum field theory. So it's a very general purpose thing. And sometimes when I'm sitting on an airplane or something, and somebody asks me what I do, I say I'm a quantum field theorist. Because that's what I care about. I care about the language more than I care about the particulars of these things. Or, I like the particulars too, but I work on the language. So what is quantum field theory? It is defined it's amazingly simple. And I genuinely think I can have you understand it about as well as I can in 5 minutes or less. First, quantum field theory, what is a quantum field theory? It is just a list of particles. So it's like, what stuff do you care about? Stock prices, or electrons, or photons, whatever. There's something that can change with space and that can move in space and time. So that's what a particle is, just something, a lump. Okay? And then it's a list of defining interactions. And I don't want to call them fundamental because that's actually a loaded word. It's definitely not irreducible. It's definitely confusing. But there's a list of defining interactions that are allowed to happen in space and time, and that's it. And from this, you have to use the central dogma of quantum field theory that we inherited from this guy, Richard Feynman. And I'll give you an example. So in quantum electrodynamics, which is the description that we have, the most accurate description of atoms and the way electricity and everything works in our world, Very simple. It consists of charged stuff, like electrons and protons and whatever, and light. So you can draw a little picture. What does it mean to move in space and time? You just, maybe you sit there. So that's a picture for how an electron looks when nothing happens. It just sits there. Photons, I guess they're not allowed to sit there, but it doesn't really matter. You just draw a picture like that. And the rule that governs electrodynamics at the quantum level is that the charged stuff can emit light, or it can absorb light. That's it. So what I mean is that this is one of the fundamental interactions. You can have two things emit light, or you can have a plus and minus emit light. You can have something just emit light or absorb it or whatever. That's it. And now here comes the magic trick, and this is really it. Like deep down, if you ask any professional quantum field theorists what are they thinking in their head, this is it. Comes from this guy Feynman, and it is that the probability that something will happen is given by imagining all of the ways it could possibly happen. Okay? That's it. So you have that one little thing, you send some stuff in, some stuff out, and you have one rule that it can emit a photon or absorb a photon or something, and you add them all up. Now it's easy to kind of see, it might be easy to see, that if it is possible at all, there's an infinitude of different ways it could happen. And that's problematic. But the good news is that a lot of theories are what we call perturbative, and the idea here is that the simpler the story, the more important it is to the answer. Okay? So just like you're making up a story to your parents, and you're making up the more complicated the lie, the easier it is to check, right? So you start with simpler ones. Similar in quantum field theory. You imagine the simplest scenarios, and then the more complicated the scenario, the less you need to care about it to check your prediction. So in quantum electrodynamics, this theory about how atoms and matter and stuff work, very simple. You only have this one little rule. And so if you have two charged things coming in and two charged things coming out, you want to know what the probability of this story is to be. You start with the simplest picture. And it turns out that the simplest picture involves a constant of proportionality that's basically 1%. And every more complicated picture you can imagine is 1% of 1%. So if you only want 1% of precision of your prediction, you just draw the first picture and you're done. The more complicated the picture, the harder it is to do the math, by the way. But I want to give you a sense that this is really the way the world works. And this is the story that I think we would need it's like the crown jewel of our understanding of how matter works. And this is the example of you scatter light off of an electron, and you see how much it rotates. Okay? See how much it rotates. And at first order, there's just one little picture. Okay? This picture, by the way, and you take it seriously. At the next level, if I'm only going to kind of focus on that little corner, there's only one picture to draw. And I give it to my students as an assignment, a homework assignment. It takes them a week, maybe 20 pages of algebra. Okay, you get an answer that involves an integral, calculus again, that you can't do. It's a pain. It's a terrible pain. Okay, but if you did this first, you get a Nobel Prize. And then the next level took 10 years. It's only 7 pictures, by the way. 7 pictures, but to convert those into expressions to compare with the experiment, 10 years. After that, computers. 30 years it took to get to the next order, and 20 years after that in supercomputers, the modern era. Okay. Now the good news is that while the theorists are calculating these predictions for how an electron rotates light, it also takes the experimentalists a really long time to get another factor of 10 in their precision. So luckily we're not, it kind of goes together. And this ratio here is this prediction. And Dirac got a Nobel Prize for saying this number was 2, which is this order. And then Feynman, Schwinger, and Tominaga got a Nobel Prize for saying that it was 1, alpha over pi times 1. I'll show you that. Well, we can compare this. So it's alpha over pi times 1, alpha over pi squared times this silly number. Doesn't matter. The point is, when you measure this to this, when I say it's the most precisely tested idea in the history of science, I mean, there might be other things that are more precisely tested, like that the charge of the electron and the proton are the same, up to a sign. That's like accurate to 100 digits or something, crazy like that. But this is I hope you appreciate, this is this is a non-trivial thing, 2.00231. And again, these numbers keep changing the higher you get, right? It gets deeper and deeper and deeper, and you measure more and more digits, and it keeps working. In fact, today, the System International and the NIST, the National Institute for Standard Technology, there are very serious discussions of giving up on this prediction entirely because the limiting factor on this precision is actually our knowledge of the charge of the electron, which is alpha, that 1% number. And in fact, it is so limiting that we're very seriously discussing taking this prediction as the defining characteristic of an electron and using it to define its charge. So to get rid of it as a prediction and just make it defined quantity. It's kind of radical. Anyways, this is, again, the most precise. There's no other idea in the history of science that has this much precision. So this is really the way the world works. And the Standard Model, which is this triumph of over 100 years of big, massive experiments and expenditure, is a story just like that. It's just a list of particles with a longer list of fundamental interactions, and you just glue them all together, and you're done. Well, okay. That's the good news, that it works. Today, the Standard Model of particle physics is amazingly precise. There are a few gaps, dark matter, things like that we don't know, but we also don't interact with it, so we don't really care. I mean, it doesn't affect, to whatever extent we've been able to test the Standard Model, it has come out exactly right. Okay. That's the good news. So the bad news about this story is that not only do the stories get more complicated, and there's lots of them, so there's an explosion in the number of pictures that you need to do to higher orders of precision, but also the math in these higher orders are so much harder that it takes supercomputers forever to get there. And in fact, it's kind of safe to say, it's a moving target about computational intractability, but it's basically safe to say that outside of an extremely small list of very simple processes involving very few number of particles and very, lowest orders of approximation, quantum field theory is incapable of calculating these predictions. They are either beyond the reach of our best computers, or even if you can reach it with your best computers, it's just such a mess that you can't make any sense of it. And that is a shame, because in order to do experiments like this, in order to discover something like the Higgs boson, you need to know exactly what the prediction is from the Standard Model, from how these things work. So something that happens millions of times a second, billions of times a second at the Large Hadron Collider is you collide two particles and you see four things come out. They're called jets. Okay? Why is that a problem? It happens billions of times a second. You need to know exactly what the Standard Model predicts for that probability distribution to discover that an exception has happened and you've discovered a Higgs boson or something like that. And when people first started thinking about colliders at this scale, which was in the 1980s in the US here, some theorists got together and they outlined the theoretical challenges. Like, okay, obviously the experimentalists have a lot of problem building these experiments, but what on the theory side, like what do the theorists need to do? What is math is missing to understand an experiment like that on that scale? And so outlining these kinds of problems, one of the things they pointed out in a long list, they said the cross sections for elementary 2 to 4, so that means you collide two things in and you see four things come out, have not been calculated, and their complexity is such that they might not be evaluated in the foreseeable future. They didn't just think it was hard, they thought it was impossible. And so they asked the reader to come up with estimates and stuff. Why is it so hard? This is literally a problem I could assign it as a text from my students in homework. It would be very mean for me to do that because every student would have this intuition, like, oh, you just follow the same rules, you just draw the pictures, right? Well, first bad news is that there's 220 pictures at leading order of approximation. This is the simplest it's not even the right answer, it's just like the first estimate of the right answer. 220 diagrams. Each one of these little pictures is like a half a page of algebra. You have to square it to get the right answer. You're done by millions and millions of terms. No human being will do that on pen and paper. And it wasn't done. I mean, these people thought in the early 1980s that this was literally impossible. Well, it's usually a very good motivating thing to say that something is impossible. And sure enough, two physicists at Fermilab, Stephen Park and Thomas Taylor, threw every theoretical trick they had into this, and they used the world's most powerful supercomputers at the time, and they got it. And they rushed it to publication with a beautiful one-sentence abstract. The cross-section for that means the probability, for 2 gluon to 4 gluon scattering is given in a form suitable for fast numerical calculations. What they mean by that is good enough to make a plot with for an experimentalist. What did it look like? It was 8 pages. Okay? The entire paper is this. They have a small little story about how we're going to do the details later. and we're just summing, and after all, you already know what I'm doing. I'm just summing up I'm just following the rules in the books. And this is the answer they got. And these are some big coefficients, whatever, and then there's a bunch of terms. But the reason why I absolutely love this paper and why it's going somewhere is because after apologizing for not giving any details, they end on this very optimistic and quixotic note. Furthermore, we hope to obtain a simple form of the answer that would making our result not only an experimentalist, but also a theorist's delight. I mean, and that is bold on a totally different level. Like, what on earth could possibly inspire a theorist? I mean, after all, in classical physics, if you have more stuff involved, it's more, the answer's more complicated. Like, that's what you expect. More stuff, more complicated. Of course, this process is complicated. There's 220 diagrams you have to add up, obviously, right? Right? Okay. I'm telling you this story because 6 months later, they stumbled upon a guess that absolutely exceeded their wildest dreams. They guessed that that 8-page, or was it 12-page, 8-page formula was a single line. And they checked it on the computer that it gave the same numbers. They did not prove this. That's too much work. No. And they checked it numerically that these things agreed. But if you stare at this expression even a little bit, look at the bottom, like 1, 2, 2, 3, 3, 4, okay. It's kind of easy to guess what would happen if you had 2 going into a larger number, like any number whatsoever. And to appreciate the magnitude of this mockery, when 2 gluons create 50, the number of leading order approximation diagrams you would draw for the scenarios that could happen exceed the number of atoms in the universe. And I think it's a rule that if I ask a student to calculate something and it involves more steps than they have atoms in their brain, they won't get there, right? And if this is true, if this were true, then you'd be adding up all of these little contributions, and they would all cancel out to something so simple that you should have guessed it from the beginning. Isn't that embarrassing? Okay? And it turns out this is absolutely ubiquitous. Every time somebody calculates something, they break their backs using supercomputers to calculate something heroically difficult for some experiment, or maybe just because they can. Every single time, the answer mocks us by its simplicity. And what's going on today is understanding that. And the goal, kind of, my big program, or what the community is doing today, is to understand why this is true. We do understand this particular one. And reformulate the rules of the game. Come up with something silly, like this calculate every number thing. Something that gives you, when you ask the question, if I scatter 2 particles and I see a bunch of particles come out, what is the probability? You get the simple answer on the first try. Is there a formalism like that? And it turns out there is. And if we can do it, if we can find a formalism where that happens, then you have the chance of dramatically improving our ability to make predictions for experiments in a very wide variety of contexts. And because it's not just about fundamental physics, but it's about the way we understand fundamental physics, it applies to the stock market and to biology and everything, all at the same time. It's an improvement in math in some ways. And today, this is what we're doing. This is a picture from last summer where we had our conference at the Institute for Advanced Study where Einstein worked. This is a community of people who are all working on this. And today, we do actually understand that particular simplicity, but it's an evolving dynamic thing. And I'm not going to have time to really tell you about what that looks like. And anyway, it's a lot of math. But the point is that we understand that simplicity, and we've been able to exploit it to a tremendous extent to really improve things. And it involves silly things like these 2-colored graphs and permutations. This is a picture I made. There's also a picture I kind of made. Well, it was made by an artist, but anyway. This is the idea that there's some geometry to calculate, and it involves these silly shapes, too. It's all very interesting, novel things. Not exactly hard math, but it's different. It's very different. By the way, this picture here that it got popular when my family and I went to the solar eclipse in 2017. My mom called me over and she said, "Hey, there's some guy over there wearing your picture on his shirt. Do you know him?" No, I didn't. Turns out I didn't know him. Just had it. And somebody also sent me on Facebook a while ago fans of these pictures. Geometry behind these things. And it also made it in, so maybe this is a good place good benchmark here, was this is one of the simplest calculations you can do, and it's long been a benchmark for how far can we possibly go? How far can we push this math? And this is just the simplest conceivable little example. It's so simple and so iconic that it even made it into the Big Bang Theory 13 years ago, where Sheldon was mixing different orders together. So the story starts a little bit before 1997, but it was calculated to 2 orders. This is just one little picture, not so bad, 1997, by some friends of mine. And then 2005, it got the next correction to that. Took a while. It's giving you a sense. Instead of that going from 1 week to 10 years, to 30 years, to 20 years, this is what the progression looks like today. My collaborators and I took over, I guess, around 7. We got 9 and 10 in one go after, just a few months after 8. My record was beaten, by the way, and then we set it again. But this kind of understanding and these kinds of powerful, like how far can we go, you can see it's better than, it's not taking longer to go each step. We're going order and order and order. And at this stage, we're talking about 35 million contributions, which is a big number, but it's not that bad. And I think at the bottom, so I've lost you at any point here. I want you to come back. But the reason why I'm excited about what I do and what I think what's going on in fundamental physics today is because I think it's definably in the midst of a revolution. And one of the ways, people debate about possible definitions of revolutions in science all the time, but I think one way you could talk about a revolution of science is when there's an well-established subject that is dusty and has been taught for many years the same way, and it's very important. And when all of the textbooks have become obsolete at once. And that has happened to us. Today, the experts who use quantum field theory, who still think, like me, I'm a quantum field theorist, I think about those little pictures and imagining all the ways something can happen. There isn't a better picture than that yet. But nobody who's actually making a prediction for an actual experiment is using those methods. We are teaching our students an old story. And what are they using today? They're using some hodgepodge of new stuff, that some of which is very well established, some of which is fluctuating. And I was trying to explain to the younger members before this talk, why aren't the new textbooks? Why aren't you write those? And one reason is because I would be terribly embarrassed to write a book today and find out 6 months later that there's a better way to do it. You don't want to do it when it's evolving so fast. It hasn't stabilized yet, but some books are coming out. But these are more, for the experts who are using it, who need it, than for students today. And this is the moment in history when we get to define the textbooks that will inform students for the next century. And so I think, like when I talk to physicists, I was once quoted in a book. So I was there's a wonderful, one of the pioneers, one of the people responsible for our understanding of the Standard Model, the birth of the Standard Model, Steven Weinberg. And I know him. I knew him before he died. And a friend of mine wrote a book, and he interviews Steven Weinberg, and he quoted me as being excited about what's going on in physics today. And he was like, Okay. Now, I love Steven. But the point is, the point of this story, why am I saying this? Because Steven was part of this generation. I mean, in the 1970s, 1980s, 1990s, this was the era when we discovered the Standard Model. It was a very exciting time. There's no question about, like, when you discovered the stuff that controls our universe and the particles that we see in our world around us. That's great. But you only discover those things once. There's then centuries afterwards of learning to play the game. And just like Newton, in the 100 years after Newton, nobody found a new force of nature. But they learned how to play the game, and that was not only important, but also formed the foundation of how we think about the world today. And I think it's a generous comparison, but I think this is very much like the 18th century when we've been given calculus. Calculus is great, it works, but we are only now playing with it and learning how to get the magic out of it. And it's very exciting to be part of that time. So anyway, this story, this research often feels like this virtuous cycle. And you can kind of start or end anywhere. You can live on any of these nodes at any given moment. It often starts with somebody calculating something, whether it's for an experiment or just because you can or just whatever, if usually it's something that was very recently impossible. Somebody says, nobody can ever calculate this, and somebody goes, go ahead, I can do it, and they do it. And they calculate something using all of the best methods. And then, and time again, I could show you, actually, I took out of this talk a bunch of examples of this, where somebody will then publish a 20-page formula. And 6 months later, it's a line. It's one line. This has happened so often in this field that, I mean, it's a trope, okay? So somebody, sometimes it's the same authors, sometimes it's somebody else, discovers that all of that output that they did, all that effort, gave you something that was so simple you feel embarrassed. And then you scratch your head, and this is like the longest step, where you try to understand, like, why I should have known that this 20 pages of algebra is going to give me the number 1, right? Surely I should know that. And then you think about why you should have known that. And once you start to understand it, you make a guess, and you test that by doing a hard calculation. Okay. But once you get that going and you really understand why, you then build it into better technology that gets you even further, and you start discovering. And unfortunately, this cycle is not ending, and it hasn't ended yet. So I don't want to write a textbook, because somebody's going to discover something and make me feel embarrassed. And that is a very exciting time to be alive as a scientist. So, and because it's not about the fundamental laws of our universe per se, but it applies to those. It has applications to collider physics. Yeah, they use these methods at the Large Hadron Collider. But it's also the methods being used for understanding gravitational wave astronomy, early universe cosmology, and there's a ton of very interesting and novel mathematics going on. Okay, well, that's it. I just wanted to give you a sense of some of the people and places, the community of people who are involved in this kind of revolution. Thank you very much. I appreciate it.
If anyone has any questions, I have a mic I can bring around.
Dr. Bourjaily, I don't have a question on physics, but based on my wife and I's experience, your biggest challenge is not going to be in physics, but raising 3 daughters.
Oh, they are amazing girls, and they're already. This is my daughter's first attendance to the summer school we had at the Institute for Advanced Study. They're learning. They're starting.
It seems like it's an interesting variation or proof again on Occam's razor, that we just keep sharpening the razor.
Mm-hmm. That's how, science progresses. Sometimes, I don't know, I try to avoid being like this, it's not grandiose, but like too vague maybe, but you could say that the point of science, or what is the goal of science, is to mitigate surprise, okay? That you're surprised by how the planets move, and if you understand, you can predict it, it's not surprising anymore, it makes sense. And, it's a funny thing where the surprises are happening inside the theory. That you have a machine that works, it's tested, it's great, but it keeps surprising you. And what we're doing today is understanding that level of surprise. It's like a whole level, but it's the recurring theme in science is mitigating surprise.
Well, with everything in a way, when you understand it, it becomes simple. Mm-hmm. But getting to that simple understanding is extremely challenging at times.
Yeah.
Just curious, if you are using AI or quantum computers, will that help with what you're doing, or is it?
That's a good question. A little bit and no. So the AI, have been some work on trying to recognize these patterns. So like with these simplifications where you take these 20 pages and collapse it to a single line, like the first time by Park and Taylor, that was a guess. They didn't simplify it. And people have tried teaching machines to do that guesswork. And you can easily check it. if it's right or wrong. But so far it hasn't been very productive. Turns out they have computers have about as little intuition for these kinds of surprises as we do. But quantum computing, not so much. It's kind of a safe job, AI-wise. But there are lots of ancillary things that people are using it for that's been very helpful. One of the greatest mathematicians alive today had a long discussion about how AI is helping him prepare lessons in his classes. You ask, what would a really smart student ask right now? Turns out that's a really good way to prepare a lecture. But not exactly on discovering math yet.
You had one slide that where you specified action as opposed to force. I think it was about Euler, and I bumped into that in other just kind of random like YouTube holes and stuff like that. Is there, I don't think I have a good clear question, but is that something you could rap about on like why action, which I think refers more to like the probabilities over simple forces? I don't, but just if it's something you'd like to just kind of.
Yeah, I mean, it's on a technical level, it's not that different from forces. But the idea that you're calculating one number and it's globally minimized, it resonates a bit with early ideas of optics. Like the reason why light bends through glass is because it's going the quickest way between 2 points. And the idea of like minimizing total time spent or total distance spent, that is a recurring theme in science. And in fact, so I gave all the credit to Euler, and he would give all the credit to Euler too. But there's another guy, Maupertuis, who was very annoying, and he insisted on this least action principle. He gave the wrong formula for it. It didn't work, which is why Euler, and he was also not very smart. But the idea, but he was like philosophically drawn to the idea that the world behaved so that it found some optimum and of something, and he didn't know what it was, but he called it action. And it turns out it does, right? It does, but it wasn't his formula. It was somebody else's. Euler got it right. He didn't get it right. It doesn't matter. So you might imagine, I mean, we do optimization is usually finding the best something. And it's kind of, I don't know why you'd want that to be the way the world works, but it is.
I was going to, recently saw a video by Derek Mueller, who runs a YouTube channel called Veritasium. And he did one on the diffraction business. And it was an interesting thing because, again, he brought up this principle of least action. Why the particle of light, a photon, has no intelligence. It does not know that it's supposed to bend at 57 degrees when it enters into a piece of glass and then change angle and come up at another angle. And they created a demonstration of this. And what again the quantum field theory was saying is that what we appear to see is not the individual photons going through. What we're seeing is, again, the probability. And I think to come to your, perhaps joining it now with your explanation about the most common path or the most common solution is 99.95% probable. The next probable path is 0.012% or something like that. And they actually showed with this diffraction, with this refraction, that it can actually demonstrate that the light is actually, there is a fraction of the light going along different paths. And to use the double slit experiment, there are particles of light that are passing across and hitting all of the target, but you don't pick up on them, or they're insignificant compared to the height of the probability of the things that are hitting them. And I was trying to wrap my head about, well, but how is it that we're able to view probabilities? And it's kind of like, well, because actually there is a loss, like the refraction. A portion of the light is lost through refraction, and that portion of the light that's lost is the part that's not following the probabilistic path. And so, in other words, the energy is conserved, that is, the amount of energy coming into the situation is conserved at the end, but because, and I was just trying to understand the fact that what it helps to, or your quantum field is helping us to understand, is that the world we look at orbits or we look at refraction and we come up with the principle of least action or the most efficient path. But that's standing outside of the system and looking down on it. If you were riding a photon inside that system, you wouldn't know where the heck you're going.
No.
And so what this is trying to do is actually it's where the person who's studying this topic should also be undergoing a transformation of their understanding of how the world operates. That when you shine your light you shine your pointer at the screen, there is a percentage of the light that is bouncing off and going to every location in this room. But the percentage of that is bouncing off into every corner of this room is so small, we don't see it. Instead, what we see is the 99.9% that hit the direction that you're showing, or off of the refraction rate. It's just something I've just, makes my head explode as I'm trying to come to this new understanding of the world instead of, as you say, the classical, view, but it's it simplifies, it summarizes it all, but it doesn't help you really understand how it works.
So I wish, there's, for one thing I didn't explain at all, which is why does taking a probabilistic worldview explain the atom? That's actually not so hard to understand, but there's another really important ingredient that, when you're when you're learning quantum mechanics, this is an important lesson, is about, what do you call it? I forgot. But the question is like, when you have a system of 10 things instead of one thing, and you want to know how the probabilities behave when you have 10 things all working together, it turns out that they all super collapse. They become very narrow. All the probabilities become narrow. And so this is why, when you look at big systems of atoms, like a string of DNA or something like that, you can basically treat it like a string because the probabilities become so focused on one outcome that classical physics emerges. And it's a very important thing. Otherwise the world wouldn't make sense if that's not the way it worked. But it's a very kind of, students really have an aha moment when they see how that works, this decoherence. When you have lots of quantum things all behaving fully quantum, but as soon as you have lots of them, it starts looking classical, more and more like it's not probabilities, but total determinism. And I don't know, people, I don't know what Newton would have thought. He liked particles of light, but I don't think he liked probabilities. I don't know. It's very unsettling to think that the world is fundamentally not determinable.
Yeah.
Einstein hated it.
Yeah, that's the not playing dice.
Yeah.
Concept.
But we have now 100 years of lots of, the existence of your cell phone in your pocket is built on these calculations. This is how the world works, we're sure of it. It's funny. It's unsettling, maybe. But it doesn't, but at a certain point, at least I'm no longer scandalized by the idea that my job in life is to predict not the future, but the probabilities of different futures.
Of course, Erwin Schrödinger might say that this simultaneously both is how the universe works and not,
Yeah, maybe.
because of his famous cat.
Jake, I don't want to get you into trouble, and we're all friends here, so just between us and the four walls, how stable is the funding look going forward for research and experimentation?
My Bayesian prior, all scientists deep down are Bayesian. Do you know what Bayesians mean? You start off with some estimate of the idea, and then you update it with data as it comes. So my Bayesian prior is that it's pretty stable. I think it's okay. I'm funded at least by the people who control the bombs, maintain the bombs. Those seem important, but people have lost jobs, so who knows? But I'm also cheap. So actually, I have a lot of conversations with my students about this. That I'm trying to remind them to be to really appreciate things. I work with a lot of mathematicians, and compared to a mathematician, physicists we live good, and it's because of the bomb. And but honestly, deep down, my math, what I do is very much similar to a mathematician. So, but why do I have funding to travel and to buy computers and stuff, and mathematicians have less. It's because of the bomb. That can go away. But at least on my side of things, I don't need giant colliders to do it. Now, I should probably take this moment to pause and defend those expenditures, because they're not very much. And considering, for example, the World Wide Web was invented at CERN by a physicist to share data on these particle collisions, and then gave it away to the world for free. It's good payoff. It's good return on investment. So I think it's a good thing to do these big experiments. But personally, I need chalk and laptops, and I'm okay. So I think I'm fine. I guess I led this with this Bayesian because I'm like expecting to hear about a grant next month or something. But I also don't really care. I don't know. It doesn't affect me. I've been rich, and I don't. In Europe, I had basically unlimited money. And what does a theorist do with money? They hire people. They hire people to talk to. And I had a big group. It was fantastic. Well, not necessary for me, my private life. I'll survive. I'll do okay.
Hi, Jake. Thanks for the cool talk. The diagram that replaces the Feynman diagrams, the cool tessellation pattern, is there like an intuition that a person, just wanting to get a toehold in this field might take away about that? Like, is it a representation of probabilities, or what would you say to that?
I can't actually give you an inch of that. Not deep, but yes. So the idea behind these diagrams, I'm kind of responsible for a lot of these things, but it goes back a long way, which is basically you forbid yourself from ever allowing you to talk about or calculate with or even make any reference to something that's not observable. So you insist, this is an idea back to Heisenberg, that you should somehow, one way of talking about quantum mechanics is that you forbid yourself from making up fantasies. And a Feynman diagram is a fantasy. It's a fantasy of some history that happened, right? These diagrams are not fantasies. The vertices in these diagrams are probabilities, and they are glued together in some systematic way. And because they are fully probabilistic, and they're all glued together in some systematic way, there is no fakery anywhere in this picture, unlike a Feynman diagram, which is some fantasy history. And these little pictures turns out to be pretty old. They were useful as a technology to calculate stuff. And it is kind of shocking to people that to quantum field theorists, that you can reproduce quantum field theory results without reference to Feynman diagrams. But you can, and it's been known for a long time that you could. And these little pictures, but there's something magical that happens in theories, in particular quantum field theories that apply to our world. And I don't know why that's true, but it is true. So it turns out that these pictures are extra powerful when just talking about the standard model, or gravity, or other things that work in our world. And they are less powerful in other theories. Like, for example, they're really bad at describing crystals. And a lot of physicists care a lot about crystals. These diagrams don't help you with crystals very much. But they help you understand the standard model. They help you understand electrons very well, but not crystals. So it's not everything. But the important thing is that every little node in that this is gluing together little experiments, observables stuck together in systematic ways.
So if I can restate it from my own understanding, each vertex is like the probability of an event going one particular way?
Mm-hmm.
Thank you.
Yeah.
So do these findings confirm or rule out string theory?
Oh, string theory isn't a quantum field theory. So okay, this is like a loaded topic. It's less loaded today than it has been. But one way to talk about what is string theory. One answer to that question, which is a very vague and sociological answer, is string theory is what people talk about at string theory conferences. And I have spoken at string theory conferences a number of times, and my friends too. I mean, and if you ask, like, what are they doing today? And if you ask a string theorist, I might be a string theorist, I don't know. what do? They're basically asking questions along the lines of, what cool things can I do in quantum field theory, and can I understand in quantum field theory? It's a catalog of mathematical tools that answer different kinds of questions. And basically, all the theoretical physicists today, like doing this kind of stuff, they kind of do string theory sometimes because it's cool math. But there's a kind of string theory which when I cautioned this at the beginning of this answer, I was referring to books like The Elegant Universe and stuff that were written in this very arrogant kind of grandiose, I don't know, a certain kind of arrogance that string theory would be the description of the entire universe. Nobody thinks that anymore. It is a set of tools that work sometimes and probably describes, I think it's probably a theorem that our universe looks like a string theory at high energies. That doesn't mean it's useful. It also doesn't mean it's interesting. But I'm pretty sure that that's the only consistent way of making sense of gravity at high energies. But who cares? Like, I don't know. I'm not going to... but the ontological question about, like, is gravity string theory? Does string theory explain the standard model or something? But nobody asks that anymore. That's very old-fashioned. Very Brian Greene. Sorry, I shouldn't have named names. But there were, like, I mentioned this because there were a lot of very popular books that were specifically against that arrogance. And I think everybody kind of agrees with them. Like, that arrogance was not justified. But string theory is definitely a really cool set of mathematical tools that does a lot of cool stuff. And yeah. It's a little bit, but it's also a distinction between, am I talking about the standard model, which is our world, or am I talking about F equals ma? When I'm talking about F equals ma, I don't really care if it's a real one or not. I can play the game, and I'm learning about math. Yeah.
The thing about Feynman diagrams is there's a simple way that a lot of people can understand, two electrons are traveling here and they collide and they emit a photon. And I wonder if because I've seen this before, I've seen you talking about it before, and I wonder if there are any examples like that that are useful for someone who is not studying this. Could you trace, I see arrows coming in and out, and do you understand where I'm going with this?
I can explain this diagram a little bit, but its relevance to physics is so many steps removed. For one thing, and this is also a problem, another reason, one difficulty with writing these textbooks is that these diagrams are not very unique in that you can, so it turns out that these kinds of pictures, what they do in life is like taking a volume of some shape and chopping it up into little bits. And you can chop up a shape into many ways. You can chop it up, there's no unique way of carving up, of triangulating a polygon. And so these diagrams are very powerful because they're like the little triangles or something, but they have to glue together in some way, and you can do that in lots of ways. So it's not at all like as beautifully simple as imagine every single scenario. No, it's like you have to learn how to chop something, and then you have to break it up, and then the answer kind of depends on how you broke it up. But no matter what, it's way better than Feynman diagrams because it's fewer terms, and it's way simpler. But there's like a few levels of difficulty. But one of the things about these diagrams, so it turns out some theories, scattering is dominant in the plane. So you can imagine all the particles as living on a disk, and they're going in and they're going out. This is also in string theory, but it's not a string theory. And in diagrams like this, it turns out that if you want to characterize pictures like this, you don't need the picture at all. You can just start at leg 1, and you follow the diagram in, and when you see a blue disk, you turn right. When you see a white disk, you turn left. So you go right, left, and you keep going, and eventually you're going to go out to the outside of the disk again. And what you do is you associate that with a permutation that takes leg 1 to leg 7, and then leg 2 to leg 12, or something like this. And it turns out that that list of numbers is 100% of the information. The diagram, useless. Of the information. That, in fact, you can erase the diagram. If you just knew that permutation, you could recreate the diagram. You could also recreate the answer. You could recreate everything. So it turns out that there's a class of theories where the entire math involved is just like lists of permutations of sending numbers to each other. It's a very weird picture. I have no intuition for this, but it's very powerful. And this is like the fastest, this is at the core of the fastest code anybody has today to calculate these things. Very weird. I can't explain it at all. I wish I could.
All right, let's thank our speaker. Round of applause, everyone.